Okay, hi. I maintain and co-develop a Python package that tracks dots. So if you have dots you need to track, I can help. More broadly, I want to share some lessons I've learned in co-developing and maintaining this code that's shared by a small group of researchers in different places with different projects and priorities, and a wide range of programming skill and interest as well. So, what dots do we track? We can track colloidal particles on the micron scale. We can track fluorescent particles on the nano scale that are only visible by their beacons of light. And we can track, say, single-cell organisms as they run and tumble. This example here is from one of the co-developers, Nathan Keim at UPenn in the Aradia group. This is showing the shear on about micron scale particles as they're stuck between two moving walls, and we can see them be strained and rearrange under this motion. And all these particles have to be tracked. I'm showing you but a small section of a very large data set. So this is what it looks like. Before I go too far, I want to acknowledge my co-collaborators. One of them is out there, Tom Caswell, famous here for working on matplotlib. And again, Nathan Keim, whose data I just showed you. We based TrackPy on standard algorithms in the colloidal community that were first open sourced by John Crocker and David Greer in about 1995. They implemented this in IDL, which in 1995 I think made sense for the same reasons that Python would be a good choice today. IDL allows for very interactive data exploration, and it has strong, fast image processing capabilities. But I don't need to explain to this audience why I would want to get away from IDL. And I wasn't the only one. Lots of people have been inspired by this IDL implementation and gone off in their own direction. But I think it is fair to say that most of these are more like transliterations of IDL code than proper translations or rewrites of the code. And definitely none of them have the modularity or the testing or the version control that I was really looking for. And so, as it happened, TrackPy began as two separate projects. Tom and I had the same idea at roughly the same time and began independent of each other. Luckily for us, we discovered each other's work before we had duplicated much effort, and I undertook merging the two codes together. If you find yourself in this situation where you overlap with some other researchers and it's a small use case and you wonder, is it worth the effort? I would say that it was. It was a Git nightmare, and we had to have some careful discussions to avoid breaking each other's research scripts and notebooks. But in the end, what we got for it was a shared community and all the benefits of that. The code review, a small community, but it's actually growing, and we have the shared bug reports and the shared unit tests. We get to use each other's features, and I think it's all been very worthwhile. In order to make this code usable by Python novices and undergraduates who work in our labs, we're very careful about the doc strings. We don't have a ton of prose docs. They exist. They're not great, but we can get people up to speed and working mostly independently in about a week on the code. So I'm going to walk you through an example project to show you what TrackPy actually does. This is a video of micron-sized particles undergoing Brownian motion in water. So they're just doing their little random walks. Those of you who are interested in using Python notebooks for teaching, I think this could be a great example project. And a slightly extended version of what I'm showing you is on our GitHub repo, so you can follow that right through. The first step is to get the images into Python. And for that, we have a sister project that might be of general interest. It's a general container for sequential images, and it abstracts out the different formats. So if you have a folder of images or a video or something else, you can address them all the same. It's a common interface. It has a nice wrapper here, you can see. It looks a lot like a NumPy array. It's just a light subclass of a NumPy array. It has the nice IPython display, rich display. So if you select the first frame, frame 0, you can see it as a PNG image here. And it has a little extra information. It carries its own frame number and arbitrary dictionary of metadata. The slicing behavior is really nice. You can do all your slicing that you want, and if you say you want to look at frames 10 through 20, they'll be lazy loaded. So this slicing is a little unconventional. It'll return the generator, and then you can avoid having all your data in memory at once. So this is PIMS. Maybe it could be useful to you as well. We have it for folders of images, for TIFF stacks, common in our microscopy work, for video files backed by FFmpeg. If you have a weird format that you want to use, it's very easy to extend. You just need to define a way to randomly grab a frame, and you need to define the total number of frames. And then you'll get our rich display and all of our slicing behavior for free out of our base class. So let's actually get to work. We need an image, and we need to provide an estimate of the size of the image in pixels, and then TrackPy will return a data frame. We have the positions of the features here, and then some parameters describing their appearance, which are helpful for filtering out wrong features or sorting or identifying features of different sizes in the same experiment, and then some parameters here related to uncertainty estimation. And you can see it did a pretty good job on the first try. You don't have to look too close to see that there are definitely some false positives in here, right? And so you can play with the filtering on the appearance parameters to do a better job of identifying your particles. And here I'll show you an experimental feature. This is an IPython widget that's being pulled in a pull request right now. This is not actually in IPython yet. And this is an MPLD3 plot, which means we can look at these two false positives here. I need to look at my own monitor to do this well. It's cool, right? This is new enough that I could still just sit here and play with it. Okay, so you can see these two dots here are definitely wrong. They're not real. If I raise the lower threshold on total brightness, which we call by analogy mass, we can get rid of them and do a better job. And whatever our final parameters were here to filter these by appearance, they're stored in this automatically updated property of the widget I was just using, so we can use that to filter features in all the other frames. So you can explore your data very interactively. That's the point of this. So we'll go on. Having found good parameters for tracking our features, we can do it in all of the frames or any subset that you want to slice. All your favorite slicing tricks from Python work just fine on these PIMS frames objects. And we get the frames, we get the features, say, in the first 300 frames of video. The next step, having found all the dots, is to identify which dot is which through time. And if your dots are undergoing a simple random walk, then the most likely position of the dot in the next frame is near where it was last found. So we link particles together by minimizing the total length of the links through time. And this is just part of the standard algorithm developed by Crocker and Greer. So now we have our particles tracked, and each one gets a little number to identify it through time, and with a little more refinement, we now have our field of tracked particles, all these random walks. Just to finish our science experiment here, the tracking is really done, but TrackPy includes tools for characterizing trajectories, and they're all pretty fast, and they have a nice API. So here we can characterize the random walks by their mean squared displacement, and that is related to the diffusivity of the colloids in the water, and from that we can then estimate the viscosity of water. We get 0.95. As you might know, the true value is close to 1, so success. With my remaining time, I want to talk about the more advanced features. And I think this could be generally interesting to anyone who hasn't experimented with IPython Parallel or Numba, these newer advanced features of Python, and they're wondering whether they might be worth the trouble. So one advanced feature is streaming. If you're analyzing features in frames and tracking them through time, it's inherently a sort of a one step at a time thing. So what I just showed you analyzed all the frames and dumped all the data into one pandas data frame at once. But if you can't fit it all in memory, if you have some really long video, that's really no problem. And so here I'm setting up an HDF file through the pandas interface and then going through the frames one at a time. Again, they're lazy loaded by PIMS, so we just need enough room in memory for one image at a time, one feature set at a time. Then we save that, forget them both, and proceed to the next frame. Linking the features together is a little more subtle because we allow for features to appear and disappear and then maybe be found again a short time later, so that if there's a little blip and something isn't followed, we can still pick it back up again. So this has to look back in time just a little bit, but it also only needs a finite amount of memory, even for an infinite number of videos. So this is a nice feature of TrackPy. All right, so we also have some high performance components, and there's a healthy tension in the project. Some users, like myself, are tracking on the order of 100 dots, and we need really good precision. Other users are tracking 50,000 dots per frame over many frames, much higher performance needs. But with these performance components comes extra ways that the code can break and more difficulty for newbies to install it and all these issues. So we basically configure all of the high performance components to be optional. The dream with the Numba capability is to just tag a decorator onto your pre-existing functions and have them work, but faster. And in our experience on the current version of Numba, we are not there yet. That dream is not there. You really have to write a second version of any function that you want to use Numba on if you want it to even run, let alone get the performance benefits. This was just our experience. But we did get very good free support from Continuum.io online as we were trying to work this out. And as you can see, I haven't scrolled far enough to show the verdict here, but Numba can go significantly faster than TrackPy. These numbers vary a lot. This is definitely not a best case, but depending on how crowded the image is and so on, using these extra high-performance components can be really nice. The second one we use was developed by Stephen Johnson, who you might know as a Julia core developer. Quite a few years ago, he developed the fastest Fourier transform in the West. Part of the feature finding procedure is performing a bandpass on the image to clean it up, and this does that in about half the time. Okay, and finally, we played around with parallelization. Obviously, finding features in frames is an inherently parallelizable task. Linking them together is less so. We haven't bothered to work that out. But at least finding the features in each separate frame is obviously can be done in parallel. And we can go in about 6.5 seconds in parallel on the two cores of this MacBook Air, whereas the serial takes about 13.5. So parallelization works quite nicely. Okay, so just a few thoughts to close. We're aware of projects that have benchmarked particle tracking implementations, several different implementations against the same data and run tests and so on, but none of that data that we know of is open. So it would be nice as a community to have an open set of videos or images to analyze where we could compare projects and track our own progress. Secondly, anyone who works in sequential imaging really wishes that it were easier to install FFmpeg. And if anyone is in this boat with me, I would love to sprint on trying to get FFmpeg into Conda. Maybe not official Conda today, but at least a bin star where we can do Mac, Linux, and Windows. That would be really nice. So talk to me if you're interested in that. We have a branch with Python 3 support. All the tests are passing, so I think we'll have that on our next release. And we're always looking for more users and more PRs. All of us are very responsive to questions, and we'd just love to have a larger community to be a part of. So thanks for listening.
Excellent. Thank you, Dan.